Welcome to another video. So this one's about Wharfedale amplifiers. This one in particular, Titan 12 active. I previously fixed a Titan 15. I'll give you some tips on that. And now I've spent 2, 3, 4 days on this little bugger, and it has been a bugger. So I'm not sure how reliable these Wharfedales are. Unlike the Mackies, all the power is derived from the switch mode power supply, but at a sort of mains voltage, 320 volts, after it's been rectified and smoothed. So you've got no PFC, that little transistor boosting the rectified mains from 320 up to 380. So, as I say, a powerful little speaker, all from 320 volts, DC. So these are the main transistors for the switch mode power supply. You can see twice the size of the Mackies, so they should be reliable. These insulators sit over there, then it bolts down to the heatsink. This board is the Fet Driver that drives those two big transistors. Well, this chip was suspect, so I took one out of the 15, put it in here, and it still didn't work. Put the original one back in, and I'll show you on the circuit drawing. If I ran this on my bench power supply at 15 volts, I'd get one drive output to one of these transistors. Obviously you don't get both without the the mains. I had one drive output, but this chip and this circuit was drawing 40 to 50 milliamps. And have a look at the circuit drawing. The two resistors in line to drop the power down from 320 to 15 only allow sort of 3 milliamps. So here's part of the circuit drawing for that switch mode power supply. 300 volts there, but in reality is roughly 320. And if you work out the current flowing through these to get your potential divider through 100k plus 6,800 ohms, I actually worked it out earlier, you've got 2.9 milliamps. So the switch mode power supply board can't draw more than 2.9 milliamps, otherwise that's going to start dropping too much voltage. Whilst I'll turn this over, show you what I did. I connected the mains down in this corner, and obviously the lead that sits here. As you can see, someone's been at this. They've damaged some tracks. I don't know if they're deliberately cut and then joined again after, but it looks like it's been burning around here. Anyway, forgetting that, I've left their link in. I connected my meter to the ground, one of the ground pins, and this VB, which is actually VB and 16 volts. And I had 4 volts here. So because I had 4 volts, I thought, right, this is drawing too much current. Put it on a bench power supply, put 16 volts on it, and it was running fine. This chip actually has a clamp Zener diode in it, 10 volts, but you have to supply more than 10 for that clamp to work effectively. So that's why they run with 16 volts. Anyway, on the bench power supply, I had a drive coming off one of the pins going to one of the transistors, but it was drawing 40-50 milliamps, which was too much. So as I say, I borrowed the chip off this one, put it on the 15, and it still didn't work. Got some new chips, 2 new chips, one for this 12, one for the 15, put the chip on the 15 and it started working. And then obviously put the new chip on this one as well. This still didn't work. Here's the faulty chip. Put it back in, still dead. And you can see someone had been at it with those blown tracks. Check these transistors, all blown. 2 Zener diodes, 16 volt, both short circuit. So I changed this chip, that transistor, these 2. So I've only got 3 on the bench here, there's actually 4. 1, 2, 3, 4. Changed all 4 transistors. These 2 Zener diodes, short circuit. You can see that's a shunt regulator to control the power to the chip. Change that, and that's it. This board was going. So it is unusual to have so many blown components on one board, but as you can see, someone has been at it. So I don't know the history, but in any event, changed all those components, plugged it in, and I got my supplies. So down here, this Class D amplifier, I had plus minus 70 volts for the base. This is a temperature sensor, 2 rectifiers, and then over the other side, plus or minus 35 for the treble, and then that's plus or minus 15, obviously the main rectifier there. So one caveat, running this power supply and amplifier on the bench. This is the Fet Driver Board for the bass, those two transistors at the back. That's the coil to take at the 400 kilohertz. That's the treble. This Fet Driver Board for the bass, as I say, is the voltage is supplied via this through this transistor, and you get roughly 60 milliamps, and working out 60 milliamps at roughly 15 volts, you've got 1 watt of heat dissipated in this transistor, and effectively after just a few seconds that starts getting really hot. So you can't run it for more than, you know, a few seconds in this condition. Really needs to be bolted down to the heatsink. Right, after fixing the power supply, I had no bass and no treble. Went to the treble chip, had a look at the mute and standby because I've been caught out before. This mute and standby were at 0 volts. And I know from the Mackies you need sort of more than plus 3 volts here. Tested the supply here, I had nothing at this point. Nothing there because this was at 0 volts. Having that at the same potential as the source, this is going to be turned on. So it pulls that 35 volts down to ground because that's turned on. So I had to start looking at the mute circuit. On this particular board, these components aren't fitted. So I had nothing there, and nothing there. So I can't expect any sound to come out of the treble chip. Right, for the bass, it took me ages to establish what's what. But you've got minus 70 volts, and then this protect. And you can see on this drawing, you see that resistor down there, 100k down there, 100k down there, up there. So plus 70 it's got 100k, minus 70 it's got 100k. So that's a potential divider. You'd expect this to sit somewhere in the middle, which would be 0 volts. Bearing in mind the minus 70 isn't 0, it's minus 70. So minus 70 plus 70, half of that's going to be 0. So I had no bass. I started having a look at other circuit drawings and the circuit board. Eventually found another one. There, I eventually found this Wharfedale Titan 15 active. So this is a 12, yet it seems to have active 15 components. And you can see the layout slightly different. So minus 70, look, we've got 3K9, and then a plus 70, we've got 150K. So with that 3K9, you can see this is going to be sitting down near minus 70 volts. Had a look on the board for this R14, which is a 10 ohm. On the board, it's actually marked as D28, but it's got a 10 ohm resistor in it. So that's resistor on the high rail for 70 volts, through that 150k, through the diode. Now the drawing, one of the drawings says it goes straight to the protect, but this board you can see has got D28, not R114, and it had a 10 ohm resistor, tracks damage, but 10 ohm resistor to the protect. Now to understand how the protect works, you need to have a look at this driver board to see what sort of voltage you need on the protect to get the thing going. Right, this is that Class D Fet Driver Board. So if you have a look at it, minus 70 is the 0 volt rail here, and then protect. The first component it goes to, look, this resistor, so it's a potential divider again, to this transistor, so normal NPN, and so any voltage there is going to, that side's connected to ground, so the minus 70, so ground is minus 70. If you have a look at this 5 volt regulator, there's the ground there, ground. So minus 70 is the ground, similar to the Mackies, the Mackie version 2 anyway. So that protect, if you have any voltage on that protect, it's going to be partly divided. Actually, so you can see it's going to be 1/3 closer to ground than it is the voltage coming in. So the voltage comes in, turns on this NPN transistor, and it's going to pull anything down to ground if there's a voltage here. If we follow this along, the supply is from the 5 volt regulator out. So we've got 5 volts coming to this AND gate for the Class D and this Fet Driver down there. If this turns on, it's going to get rid of that 5 volts. It's going to short that 5 volts out, short it out across this 5k resistor. So I put a wire link to this base of this transistor. When I had no base, I had 0.6 of a volt here, so this was turning on and killing my 5 volt supply down to this AND gate. So I thought, right, for the amp to work, that protect has got to be down at -70. But what was happening was actually running at -68, so 2 volts, and then 2 volts difference and half a volt there, killing this output. Right, you'll see here, this protect and -70, I started looking at this and the mute, and I got confused for days. I thought, well, that's a PNP, so to turn this on and get any power out of here, you have to obviously take the base voltage away or make it lower than the emitter. And no matter what I did here, in the end I shorted this directly to ground on this optocoupler, and I couldn't get any voltage out here. Well, these were some notes I did. I just captured part of the drawing, started writing down what I had. So look, -67 and -69 on the protect and -70, so that should be turning on. But look, you can see the base was at 14.5, but all I could get on the collector was 0.4. 0.4 down here, through there, through these, and 0 volts here isn't enough to turn this opto isolator on to pull this supply down, pull the protect down to the -70 volts. That has to turn on. If I can zoom in, that opto isolator has to turn on to get rid of this protect voltage and bring it down to -70 volts. As you've seen on the transistor, on the protect circuit on the driver board, if you've got 1 or 2 volts sitting on the protect line, 1 or 2 higher than -70, that driver board isn't going to run and isn't going to run the base. So when this is activated, whatever supply we've got here is going to be pulled down to -70. The -70 is not going to move, but the protect is. And if you have a look at the protect, so we've got +70 coming into this 150k. So if we pull this down to -70, all the voltage would be dropped across the 150k. You can see on this section of this amplifier that I cut, this needs to turn on. We need a positive signal, so more than 1 volt to turn this LED diode on, this optocoupler. So we need more than 1 volt there to turn this on, to pull this protect down to -70 volts. So you can see, whatever it's going to, if it turns on, it's going to pull it down to -70. But on this protect here, I had 2 or 3 volts above that. So I thought, why isn't this turning on? And then back up to the rest of that circuit, which are these transistors in this corner, and the optocoupler is just in the corner there. So you can see, testing it here, look, I've 15 volts in, 14.5 the other side of this 10k, 14.5 here, but only a 0.4 here and 0.2 there. 0.2 isn't enough to turn this on, and all I had here was 0.7 of a volt. 0.7 isn't enough to turn that opto isolator on. They need a forward voltage of about 1.5 volts. So I went back to this mute, which had 0 volts either side of this resistor. So the protect -70. So initially you need the protect higher than the -70 to turn this part on. When it turns on, you actually get 7 volts here. But why this wasn't turning on? You think, right, where does this mute come from? Well, these drawings are right headache, because as you've seen, there's discrepancies on the board and the circuit drawings. So what am I on at the moment? Titan 15. So if I go back to the 12, And just to reiterate, you can see this 12 is wrong because it's not showing that resistor here, but I have got that resistor, so that's why I've been using a 15 drawing. So go back on this 12. There's like stop controls, not sure if they're on the board, but if I scroll back up to the power supply, mains in. So I measured this more than once. Minus 15 here, and you can see mute to page 4. It says to page 4, it's actually to the section 4 of the circuit drawing, not page 4, because look, we're already on page 6. Don't know if you can see that. So the whole lot's confusing because this board looks like it should. This board has got 15 components, not 12. But yet some of the parts on the 12 are correct and some of the parts on the 15 are correct. Anyway, so I'm now on the active 12 circuit drawing. Back at that power supply, you can see this optocoupler, and you see we've got minus 15 on one side. So when the mains turns on, you can see the AC, so it's rectified, and it charges this capacitor. And if you have a look, 22k and then 4k, work out the current through there, it's something like 8 milliamps. So you get 8 milliamps current through that. That should pull this down to minus 15. You can't test it with diode test, you have to put your meter on resistance and power it up and see if it turns on, like closes the switch. I kept on measuring 0 volts here and minus 15 there. Why isn't that turning on? So, how I eventually concluded this was faulty, you can test this input with a diode test and you just get just over 1 volt drop across that diode, and the input has got a spot on one end. What I did is put my meter on voltage, stuck the 2 pins on there, so with it powered on the mains, you should only have like a couple of volts there. You see this 10 microfarad 100 volt capacitor, but you know, that's a diode, you're not going to have more than 1 or 2 volts across it. Put my meter on it and it was flicking up and down to 200 volts. I thought, well, 200 volts is going to kill that, but really, looking at that, the resistance through there, and then down to the ground, you're not going to have 200 volts. There should be only 1 or 2 volts. So because I had 200, I figured, right, that current or the voltage travelling through there isn't being pulled down. I'm just measuring neutral and live with no load. So really what had happened is this diode had gone open circuit, probably where it had been butchered before. So I changed that, measured it again, and just had the 1 volt. I actually swapped it in the end. Fortunately I had one. Swap that pulled that down to minus 15, which pulled this mute down to minus 15, which pulled this JFET gate down to minus 15, so that turned on and gave me 7 or 8 volts supply on the mute and standby. And going back to the first drawing, once that minus 15 was active here, this turned on, that turned on, and this protect came down to virtually minus 70, which sits where the minus 70 rail is. So there's less than a volt difference. So that wasn't working, the treble wasn't working, I had no bass output because of the protect was sitting high, and the protect was sitting high because the optocoupler around the mains was blown. There were lots of, I think one of these were blown, the Fet Driver Board for the switch mode power supply was blown. Someone's definitely been at this, and this hasn't been easy. But you can see here, for this to ever turn on, that initially has to be higher than minus 70, otherwise this will never turn on. That has to turn on, pull this down to ground, or that's virtual ground. There's a 2.2 ohm resistor between this ground and earth. So this has to be higher, the protect has to be higher than minus 70 to pull this down to turn that on. You get more than 0.7 to turn the second opto isolator on, and then the minus 15 comes in. You get minus 15 here, and this actually sits around 7 volts once it's all running. So it's actually quite complicated, but I can see why they've done it. Right, so I've got my negative probe on ground, proper ground, and the positive on -70. I'll turn it on. -71 volts on at -70. So we need the protect to come down somewhere near -71 for that Fet board to be enabled. Don't forget that transistor that supplies the current to this board will be getting hot, and mine is already. It's got to be a good 30-40 degrees, and it's only been on 10 seconds or so. So that's the -70, which is -71. So we know from the circuit drawing that protect has to be pulled down to -71, otherwise it's going to disable this board via that transistor I showed you. So this is the protect. Turn it on for a second. There we are, -71. When this wasn't working, that was 69, 68 volts. So we had 2 or 3 volts difference, and that 2 or 3 volts turning on that NPN transistor, disabling this driver board. This is the standby and mute for that treble chip. I had something like 0.1 of a volt before. So let's see what we've got now. I've not actually measured it. 12.9 volts, so it's pulling that 35 down to 12 by having that -15 on that junction FET. What I'll do now, put my meter here and show you this voltage is pulled down via the protect and -70, and once it switches on it will stay on. That's the optocoupler in the corner. That's the ground I've been shorting everything out to. That's the ground. That's controlled by one of these transistors. And you see the protect, which is this side. Protect and -70 is this side. We'll see what voltage this comes down to. I'll turn the power on. 7.8. Don't forget that transistor is going to be cooking, so I can't leave it on. Alright, now I've hooked up my signal generator. Let me turn the input. I haven't got a filter capacitor to take out the 400 kilohertz, bearing in mind it's a class D, so this is now, the scope hooks up to the output. Let me turn the amp on, and you can see that's the base. Turn it up quickly before that transistor overheats. 300 millivolts in, we've got 56 volts peak to peak coming out, and none of it's on heatsink, so I can't leave any of it turned on. So hopefully this has given you some insight into fixing a Wharfedale 15 or 12 active powered speaker. Thank you for watching.